Hello, good morning to everyone. We are pleased to welcome you in our new plant. This is the new plant of EMAG SU, the company that is basically formed by the former Samputensili and CLC companies that EMAG acquired in 2021. So we are now presenting you the companies and the new factory and plant. The acquisition started last year, and one of the main ideas of the acquisition is for EMAG to being capable to propose on the market a complete set of processes that are used on the gear business in order to produce from a blank to a completely finished part the complete gear teeth involute. So we see in this chart how basically the products of EMAG SU are entering. So EMAG was already very competitive in the proposal of standard turning, already hobbing with some EMAG Kopfer, debarring, hardening, and laser welding, and now with the products of EMAG SU is capable to reach one of the main targets and mission of EMAG to present a complete line for the gear products with the addition of some cutting machines, hobbing and shaping, and basically also with the addition of the Samputensili grinders at the end of the gear process. So again, I mentioned we are happy to welcome here in the new plant. This is a new technology center. In this center, we are basically collecting the previous two companies, Samputensili and CLC, and we are operating here since the beginning of May of this year. We have already started to delivering machine from the new plant, and we are having inside all the activities related to the EMAG Technical Center for the gear business related to EMAG SU products. So we are having design, engineering, we are having assembly, final pre and final acceptance testing of the machine and testing of our products. So we are happy to present our plant and basically also to enter a little bit more in detail of what are some proposals that we are having for the electrical transmission, for the eDrive, for which we have developed some dedicated solutions which we want to present you sorry, together with the tour that we will make at the end of the video in order to show you live some of our applications. Sorry. At the end, we will give you the possibility to place some questions, and we will be happy to answer to those questions. So, lastly, I didn't make it at the beginning, I do it now. I am Enrico Landi, I am the General Manager of EMAG SU, and I present also Alex Morard, who is our sales technical expert and manager for the German speaking market, to which I leave the word to show you the news that we have in the eDrive component proposals. Thank you very much.
Okay, also welcome from my side. We are staying here direct in the production, so when you hear some noise, this is coming out of the production which is around us. And I want to give you a short overview over the products we have, and then I will tell you something regarding especially the grinding machines. And then I will skip over to the technology, so I want to tell you something regarding meshing, dressing, topological grinding, polishing and fine grinding, and at the end some reduction of noise regarding surface structure. And then I want to give you some examples of electro components we have ground. And then I want to give an outlook what we can do in the future. So first I will start here with the products we have. We are producing hobbing and milling machines, also for eDrive components. These are the machines CLC 200 and 300. Then we have deburring machine, shaping machines, shaving machines, and we are producing, of course, generating, grinding and profile machines. You will see also in the shop floor when we make the tour here these kind of machines. First, I want to show you what we are talking today. We are talking over an eDrive components. So here are typical workpieces for these eDrive components. So it's a ring gear, an input shaft, a pinion, and an intermediate shaft. And first, we will look on which kind of grinding machines we can produce these kind of gears. So you can see here our two machines. It's a G160 and a G250. G is staying for grinding, and the number behind is the maximum diameter we can show on these kind of machines. Here on the G160, the operator is staying here. This here behind the bedien, the swivel control panel, there is the door for the automation, so loading and unloading, and we have a swivelable control panel that the operator can use it on both sides. This is a high productive machine, very fast, and this has a ship-to-ship time less than 2 seconds, and the module range is between 1 and 3, and the shaft length is maximum 300 millimeter. On the G250, the operator is staying here. We have also here a swivel bedien panel, and here is the door for loading and unloading. This machine has a tower with 2 spindles, so which is turning around for loading and unloading, and has a ship-to-ship time for less than 5 seconds, and the module range is between 0.5 and 7, and the maximum shaft length is 550 millimeters. All the grinding machines have a Siemens control. Only the hobbing machines can be ordered with the Fanuc and the Siemens control. But here on the grinding machine, we use only Siemens. That's something to do with a lot of interpolation we must do during the grinding process, so we need the capacity of the Siemens controller. Here I want to show you the architecture of the G160 machine. And here on the grinding head, you see that we have only 3 axes on this machine. So it's a Y and Z and the swiveling axis for the head. And you see one axis is missing, the tangential axis is missing. How we do the shift operation in the generating grinding, here we have an interpolation between Z and Y so that we interpolate these 2 axes so that we have a shift axis. This kind of architecture makes these machines absolutely stiff, mechanical stiff, and also a dynamic stiffness. One of the big advantages that we didn't have this tangential axis, and also there is no wear in this axis because normally the space for this axis is very small, around 100 millimeter, and the pressure on this axis is very high, so we didn't have this in the machine. So this is really a stiff machine. On the table side, on the other side, you see we didn't have here an X-axis to move the grinding head to the parts. We do this in another way. We drive with the spindle to the grinding wheel. And so we have here on these 2 iron cast blocks, the 2 direct-driven spindle. And below these spindles, there are linear motors so that we can do the movement next to the grinding wheel in a really short time, and also without any wear in this component. So what is the advantage of this machine that you can see here? This is a view of a conventional grinding head. And here you can see the distance between the swivel point and the tip of the grinding wheel is in the conventional head is 480 millimeter. And on the G160, it's over 110 millimeter less. Here the distance between the A-axis and the point of contact is 370 millimeter. what is the biggest influence we have on the grinding side? You can see here on the left side a picture we have made from the surface of a gear. And what you can see here, when we have here this tangential axis, which is located here in this area, you can see that here is you can see some effects from a frequency. We call this ghost frequency, and these ghost frequencies are not so high. They are only in they are between 1, 2, 3 microns, not more. But they have an influence on the noise behavior of the gear. These small waviness create a noise in the gear. And when you see here, comparison to this picture, this one from the G160, that the frequency are nearly gone. So this influence is much better, and especially for these electrical components, which are running with really high RPMs, the noise behavior is really important. This noise behavior is regarding 2 points very important. The main reason is we didn't have a combustion engine, so there is no noise around. And with the higher RPM, the noise frequency, it's much more in the area which we can hear. And so it's absolutely necessary to reduce noise in these kind of gears. Here is now a short video of the machine. I make it a little bit bigger. So here's the part, here's the grinding wheel. And you see we are grinding now this small pinion, in this case here on the spindle, making 2 passes, a roughing and a finishing pass. And you have seen before how short the time is between one spindle and the next spindle. So this is 1.6 seconds, so we are really fast. And what is the advantage for the customer? Normally we have a ship-to-ship time on a machine which is between 4 and 5 seconds, so we are 3.5 seconds faster on this machine, only with the jump from one spindle to the next. And when you grind such a small gear as here, we do this under 10 seconds, and you can reduce the time over 3.5 seconds only with the ship-to-ship time. Then we are between 15 and 20% faster as on the conventional machine, and this makes this machine so interesting. I think this is the fastest generating grinding machine you will find on the market. Here below the gear, of course, is the balancing system integrated, and also we have an NC controlled oil nozzle so that we are really in a good position for cooling this process during grinding. So now I will jump to the technology. I want to tell you something regarding meshing, dressing, topological grinding, fine and polishing grinding, and noise reduction with an optimized surface structure. So here you can see on the left side the meshing of the G160. So the inductive sensor is directly placed behind the gear, and this can be set in diameter and in the height, so that we can set this directly to the gear. And of course this meshing is meantime parallel, so we need only some RPMs that we can mesh the gear and bring this together with the grinding wheel. When the first part will come in, there we have an automatic cycle. For example, when the tip of the grinding wheel hits the tip of the gear, then we can recognize this over acoustic sensor, and then we move the part half of the gap below, go in the slot with the grinding wheel, touch it on the right flank, on the left flank, go a little bit deeper, do the same thing, and then we have an automatic meshing for the first part. The second one will be done with the inductive sensor. On the G250 we have a 2-table concept, so it's a tower with 2 tables, and in the loading and unloading station we have a swivelable meshing sensor which is swiveling in, then do the meshing, swiveling out, and then the tower turns again to load and unload the part and bring the grinding wheel in production. Also here we have the automatic cycle I've explained before. Then we come to the dressing. Normally the eDrive components are running in mid-side or bigger batches, so we use only 2 kinds of dressing rolls. So we have a multi-rib, The multi-rib is a dresser which dress all the starts on the grinding wheel in time, so it's the shortest. We get the shortest dressing time, and this is more for mass production when everything is clear, the profile, form, and the modification on this flank form. And then we have also here the full form roll. The full form roll is also dressing here the right and the left flank and the tip. And here we drive through every start. From the cost, of course, the multi-rib is a really cost-intensive tool. The cost of the multi-rib, of the full form roll is lower. And also we use this full form roll for doing dressing for the topological grinding. And this is the picture on the right side. Here you can see our grinding worm, and you see we have split it into 3 sectors here. We need this sector because during the dressing for topological grinding, we are driving with the dresser diagonal through the grinding wheel, and so we have here some areas which we are using for dressing, finishing and finishing. So this is a little bit different from the normal process, in production. When we grind a normal gear without any modification in twist, then we do a roughing pass, then shift a little bit, do the finishing pass, and when the next gear come in, we do the roughing pass in the same area we have done before the finishing pass, then shift a little bit and do then the finishing pass, and then we are going along the face width of the grinding wheel so that we use it before we dress this again. Here in the topological grinding, it's a little bit different. We are driving because we must set the pressure angle during this grinding over the face width. We are driving always through these sectors. So for roughing, we are driving completely through the sector, jumping to the next sector, and then doing the finishing pass. And for the next gear, we're starting with the roughing pass in the same sector and shifting through this period. This has, of course, an influence on the grinding time because the number of parts in topological grinding are less as it is in the standard version. So here we must dress more often as it is in a standard process. So also the topological grinding is not for free. This costs something. But we have a big advantage here in our machine. I've mentioned before we use a standard tool, so you can grind normal gear with this dresser and also topological ones. It's not necessary to change the dresser, and also the dressing time is on the same level. So for a topological grind part, we need 3.5 minutes for a 3-start wheel and 5.5 minutes for a 5-start wheel, which is similar to the standard process. Okay, let's jump to the topological grinding himself. First, I want to give you some cases regarding the twist in the surface. And you see here we have a shaft which has a helical gear, and we are making a crowning over this gear. And when we are doing this, we are driving back with the x-axis to bring this crowning in the gear. And when we do this, we get a twist in the surface. And you can see this here when 2 gears are running together, a gear and shaft, for example. On both is a negative twist. And you see that these edges which are connecting here together have a high pressure in this case. And this increases the wear, of course, in the gear, and also the noise behavior. And with the twist compensation, we are now able, for example, to make the opposite twist. So we turn this twist here in the opposite side, and when the gears are meshing then together, it's much smoother as it is when we have this situation, and this reduces noise. And of course, we can do twist free so that the flanks are going parallel together. This is a possibility, or we can do this in the way that one side is maybe the opposite twist and the other is twist free. Here we are absolutely open. So what must we do in the grinding wheel? You have seen the picture before. This was our wheel I've shown you before at the dressing page. And now here, this is the grinding wheel himself. And you see when we want to make it twist free, we must bring this edge here to this position. So we must change here the pressure angle. So in this area, when we grind in this sector, we must have another pressure angle as when we are doing with this pressure angle here, this compensation. So we must shift completely to this sector to set here the different pressure angle we want to have. And with the dressing diagonals through this grinding wheel, we have this effect that we have a very constant variation in the pressure angle, and so we can compensate these twists. We correct normally twist only in the profile form. Automatically, it will have an effect on the lead. So this is directly connected, and it's only necessary to make modification here in the profile form. How does it work on our machine? This is here a picture of our HMI on the machine. And you see we have split it in two sectors. Here is the sector where we can put data in, and here we have a visualization. And as I mentioned before, here the operator can choose what he wants. He can show the natural twist, which is normally coming out of the effect I've mentioned before. And then he has the possibility to choose natural, he can choose twist free, the opposite twist, and different twist on the right and the left flank. He can see the result here on the screen. And what we are doing when an operator wants to grind a gear. So he put it on a machine, and then he say, okay, I want to make this, for example, twist free, and choose this in our HMI. And then the machine calculated, and he can check this on the visualization. And this is the result which is coming out regarding our internal calculation only from the machine axis. And then he can say, oh, here this is minus 4.6 microns. This is a little bit too much. I want to correct this maybe in this direction. And then he can give here the correction in, and checks this directly here on the visualization what he have done, if he have correct in the right correction. Okay, and when this is fine, then he want to start with the first gear, so he grind the first gear, bring it to the measuring room and come back, and then he say, okay, I want to correct only 2 or 3 microns this area here in this direction and this in this direction. And he can put the data in there, and then he make an additional calculation and can look on the visualization if he have correct in the right direction, and then starting the second gear. And I think then it's fine. So what is the advantage for the operator? The setup time is very easily, because before grinding a gear, he can check what he have done, if he had done the right corrections. And so the setup time, it's much lower as it is when he first grind in the wrong direction and then correct it again. So it's very easy and useful for an operator to make corrections and reduce setup times, so that you have at the end more productive time on this machine. So I think this is a big advantage regarding this easy software we have on the machine with this kind of visualization. What is coming out that you can see here on this graph. On the left graph you can see a chart with a natural twist, and on the right chart you can see we have done different corrections. On the left flank we have the opposite twist, and on the right flank we have twist free. And this is easy to set up, I've mentioned before. And when you think over this, we have done this with the full form roll, which have a 2-flank contact, and we dress also the tip. So it's not only diagonal driving through the worm. Every axis during the dressing operation is moving to create such a result. So there is a lot of mathematics behind to get this fine result. Also, when you look at the quality, I think this looks very good. Here also on the twist free, you can see really parallel lines, and the opposite twist looks really like the opposite twist as it is on the other side. So I think this is a perfect result. Now we are coming to the modification in the surface roughness. And here we have two possibilities to do this. First, we can do this with fine grinding and then with polishing grinding. Here in polishing grinding, you see on the left side the grinding wheel with the blue area. These are two ceramic wheels which are glued together. And the red area, this is the roughing. This will be used for the roughing pass. And on the left side, the white one, is for the finishing pass. So also here we do two strokes. First, we are doing here the roughing stroke and then jumping here to the finishing area and make the finishing stroke. This has a grain side of 80 and this is a grain side of 400. What is coming out here? So here we can see that the RR value is here 0.16 on the right flank, and on the left flank it's RR, it's 0.17 microns. So it's a really good result, and in the mass production we are with this process every time below 0.2 microns, so it's really a good surface. Now we are jumping to the polishing grinding. Polishing grinding, you see also here a grinding wheel. This is also the blue one is also a ceramic part, and this is glued together with the resin wheel on the other side. And the process here is that we are doing here first a roughing pass, then shifting a little bit, do the finishing pass, and then jumping to the polishing area and do the polishing operation. And when you look here at the gear and on the surface, there is another word in the English language, it's mirror grinding, and it's really like this. When you look on the surface, you can see the opposite side of the gear, so it's really a fantastic surface. And here for this gear we have ground here, we have had a floor time of 67 seconds. What is the big difference between fine grinding and polishing grinding? Of course, it's the surface, it's here much better. But on the finish, with finishing grinding, you have only two passes, and here you need one pass more for the polishing stroke. But first, we want to look what is coming out here. So also here we have RR, which is 0.12 on the right flank, and RR 0.11 on the left flank. So really a good result. And also in mass production, we are definitely under 0.15 microns here in this case. But I also want to say something regarding the quality we get out here. This is a typical part for an eDrive. And you see here the result is really good, especially here when you look at the runout. The runout is really perfect, and this makes these gears also not so noisy. Because when the runout is really bad, then you hear this in a gear. It's like a sound, like a frequency you can hear. And also when you look here at the FF alpha and FF beta value, these are also very low. We are normally under 1.5 micron with FF alpha and FF beta value. So this is really a perfect gear, I would say. With the polishing stroke, we do something. We cut the peaks in the surface away, and you can see this here on the surface measurement we have done. So when you look here, all the peaks are gone here, and only holes are in where the oil can sit on and have a good running with the two gears together. And the polishing stroke eliminate all the peaks. So when we starting to run off the gear together in the first runoff, this has an influence on the wear, because the peaks are creating wear, so that pitting is starting, and we reduce this here. And the big advantage here is that we can send more torqueway over this kind of gears, and the noise behavior, it's normally better. I must say normally better. We have some cases where the noise behavior with polishing grinding is not better as it was before. So here it's not 100% for noise reduction. capable this process. Then we have the possibility for grinding gears with noise optimum grinding. On the left side, you can see a picture of a surface of a gear, and what you see here, that the remarks, the texture of the surface is going completely over the flank line, and they are also parallel to the axis. And this means when you have the same remarks on two gears which are running together and they are parallel, they create noise regarding the parallelity of these scraps you have. And with this software, we can change the angle a little bit and we can shorten these remarks. And when you are having an angle between the two gears, when they are meshing together, the noise behavior is much better. And also when these scraps are not going over the complete lead line, then the noise behavior is much better. So now I want to show you some examples. I have two examples here in the presentation. One is on the G250 and one is on the G160. So you can see here ring gear which we have clamped here and with a pressure belt from the top, so that we have a stiff clamping fixture here. And this is a clamping fixture with this expanding and then brushing from the top, so that we have a stiff clamping here. And here we have 88 teeth with a module of 2.1 and a pressure angle of 20 degrees and a helix angle of 25. And the tooth width is 35 millimeter and the outside diameter is 206 millimeter. We achieve here a Dean quality of 4, and the floor-to-floor time was 96 seconds. And this is including 69 seconds, and it's including twist compensation and the proportional of dressing time. So the normal grinding time is 59 seconds in total. I've mentioned before that with the twist compensation, the number of parts is lower as it is in the normal grinding. This has something to do with the sector, that we every time with the same sector are driving through the same area of the grinding wheel. And after a while, when they were starting in the grinding wheel, the FF alpha and FF beta value increase, and so that's the reason why we didn't have so many parts between two dressing. Here is a chart of this. This is a gear which is not so much compensated, so you see a crowning in the profile and in the lead. And also here you can see the perfect clamping, so the runout is really, it's more aligned, it's nothing else. So FF alpha is also here very good. It's in the profile form, it's 1.1 microns, and in the lead it's also 1.1 micron. So it's a really good result from the for generating grinding. Here is an example for a G160. It's number of teeth 21, module 2.1, pressure angle 20 degrees, helix angle 25 degrees, tooth width 37 millimeter, and the outside diameter is 55 millimeter. Also here we get quality for floor-to-floor time 34 seconds, also including twist compensation and proportional dressing time. And the grinding time was 25 seconds. What we have done here with the clamping, this is a small gear. So we have a friction cone here below the part, and we are clamping here with the center from the top. And with the friction cup, we are also able to clamp really stiff small diameters, so that we have really a big effect regarding runout. And there is a movable center from the bottom, which press the part afterwards out of, so that we can load and unload this with the automation. Also here a result. This is a gear which is much more compensated. So you can see here which much more modification. So you can see here in the profile form that we have a conicity combined with the crowning. This is on the left side stronger as it is on the right side, and in the lead it's absolutely the opposite. So the modification on the right side are much more as it is on the left side. But here, also with the friction cup, you see the runout is really perfect, and also here the FF alpha value and the FF beta value are really on a poor level, so absolutely nice quality, I would say. So now I want to give you only a short outlook what we have done in between with dry grinding. So we have here a process which is capable to grind without oil. How does it work? First we must make, instead of the rough grinding, we have here a skive hobbing as a process in. When you want to remove much material with the grinding wheel, it doesn't work, because then you have burnings in the gear. But here with the skive hob process, this is more cutting. We remove the heat out of the part so that we can use this as a roughing process. And the dry process with the generating grinding wheel works when we have less stock on the flank and when we have a really high in speed, so that the ellipse form which is going over the surface during generating grinding didn't have enough time to bring the heat in the part, and then it works fantastically. Afterwards I show you a video how does it works, but I want to give you also some ideas why we are want to implement this dry grinding process in the market. And there are some reasons. First, it's the smaller footprint. Normally the filtration unit for a wet machine, it's much bigger as the G160. So here with the vacuum system we have next to the machine, this is much smaller as the filtration unit. So we need maybe half of the space as we are using for a wet machine. The tool costs are on the same level because we are using here the expensive tool, and this is a dresser, only for resharpening the grinding wheel. And so this compensates the lower tool cost for the dressing roll, compensates the tool cost of the skive hob. So we have the same tool costs here in this machine as it is on a wet machine. And also from the process time, we are on the same level as with the wet machines. Sometimes we are a second faster, sometimes we are a second over the wet grinding process, but in total this is the same process time. And we can save here a lot of energy. When you see in a wet grinding machine, 75% of the energy will be consumed in the filtration unit for high pressure and cooling the oil, and of course for the healthy and safety of the employees in your company. Dry processes are really an advantage regarding the wet operation. So here's now the video. What you can see now, we are doing the skiving process. So the gear is coming in after the heat treatment process with hardness of 58 to 62 HRC. So now we have removed, maybe when we have a stock of 100 microns, we have removed 90 microns with the skive hobbing process. And now we have skipped to the generating grinding process, and we are removing now the last 10 microns to make a nice surface. Also here you can see the short ship-to-ship time from 2 seconds. In between we have load and unload the part and do the meshing, and now it's waiting and ready for the next one. And now after the skive hobbing process is ready, we are jumping back to the grinding process. And now here you can see this in real contact. How does it look when we do this kind of grinding? I must say also something regarding the quality which is coming out of this machine. This process is the first grinding process where we have a constant stock before grinding. After the skive hobbing process, the stock is always the same, and this is also the result of this machine. The parts are looking really similar regarding quality we get out. So now I think we can make a tour. I'm ready with this presentation.
Thanks a lot, Alex, for your detailed presentation of all our proposals for the eDrive. Now it's time to really see the new plant that we have, the new plant that is running. Of course, now is late in the afternoon, so maybe we are not 100% fully loaded, but at least we can show you the plant. Here we have the measuring room, where we are basically certifying the quality coming out from our machine. We have an involute measuring machine, we have a CMM 3D machine, as well as we have available a roughness measuring machine, which is capable to measure all the delicate items that are requested by the eDrive components, like the roughness coming out from super finishing processes, and so we are, let's say, capable to qualify properly the gears. Here we are in the assembly area, for example, in the vertical generating grinding machine assembly area. Here we see a model of a G250 that we have shown you also before. You see the machine, how does it look like? We have completely assembled the machine in our plant. You have a double table solution, one table in loading station, another table in grinding station. The meshing unit, which is in the loading station, so can run in parallel time, as well as the grinding side with the counter support, which fits a very large generating grinding wheel, an NC actuated oil nozzle, and the machine is almost finished to be run off. This machine, together with this other machine that we see in a previous stage of assembly, is basically part of a project that has been sold to an automotive customer, where EMAG has finally proposed a complete line after the heat treatment process. So a line which is comprehensive of hard turning, laser welding, additional processes, and finally the generating gear grinding. So this is the mission, and the idea of EMAG to being capable to provide a complete solution is now put in place. We have other machines here also available and in assembly. For example, this machine that we see here, it's a kind of old process, but still actual process. This is a shaving machine. It's a shaving process. You see the shaving process basically is using a tool which is preformed, like the very near to the final profile of the part that have to be produced. It's a process that is finishing the gear before heat treatment. It's still one of the most is still one of the cheapest solutions to finish a gear, but in this era of the eDrive, it's a process that can also be used to improve the quality of the input quality of the gear grinding process, because the gear grinding process has been requested to reach much higher results and performances. So the better is the input quality, the better is, of course, the final result. Yeah. Here we move in another area of our assembly, where we are assembling the profile grinding machines. We have different sizes of profile grinding machines. Here you see a model of a G375, is one of our, let's say, most produced machines, most present in the market, as well as we have on the opposite side the largest size of profile grinding machine. It's a 4-axis machine, 4 CNC axis machine that is capable to grind rotors or screws or big gears for different field of applications, rotor for compressors or screws for hydraulics, and so on. Here you see one of our most flexible solutions, again, of profile grinding machine. In this case is used to grind a screw pump, so the profile of the screw, and this is a machine that is basically providing all the full options of the profile grinding capability from the definition of the profiles, and it's quite and a very big wheel for a low tool cost, and it's quite, let's say, as a machine, capable to be to have a flexible configuration. In fact, here we can show the same machine that can grind a screw like this, which is a so-called double helical screw of different sizes, but a similar machine configured in another way, like this one, where we have, for example, an additional fifth axis CNC actuated, which then becomes a suitable machine for a large variety of applications and a large variety of gears, for example, for the field of aerospace. So the aerospace is trying to create and to propose a lot of different type of gears, compact form, very high precise requests.
And normally with a lot of interference, of course.
And normally with a lot of interference to have compact gears. And so we need a very small grinding wheel, but also very big grinding wheel for different gears. And in a different configuration, as you see here on the machine, we have an external spindle. On the table here, we have another option, which is an internal grinding arm, which is capable to grind the internal gear. In this case, is straight, but we can grind also helical internal gear.
Yeah.
And we have this kind of unit, which can be equipped with different size and variety of internal grinding arm, from a wheel that can be as a standard from 150 down to 30 millimeter, but in special cases also be properly designed to go even lower than 20 millimeter diameter grinding wheel. So we see also here some other example of applications that we can grind. In this case, we are not grinding the bevel gear, but we are grinding an internal spline that is done from solid in some applications. For example, the aerospace, some of the features are ground from solid in order to be, let's say, sorry, in order to be optimized in the process. Here we can show some other examples of product that can be ground on our horizontal profile grinding machines, like screw for gearboxes, for worm wheel gearboxes, or a rotor for a compressor.
And of course, we can also do the milling operation for these kind of parts. So we have milling machines for big rotors, as we see next. As the next, and also here for the worm shafts we can do the milling operation, and here we have also high productive machine. Also on the grinding side we have special machine for making big batches of these kind of screws with a double table concept and a profile wheel.
Yeah. So thanks, Alex. So as he mentioned, we can also make cutting, so milling machines and hobbing machines. So here you see, for example, in construction, a machine which is basically put in line with the previous big profile grinding machine. This is a rotor milling machine, so it's a very stiff basement with very stiff axis and movements, which will be built and put in line with our profile grinding. So for this type of components, we are capable to basically provide the complete line from milling to the final grinding operation. And also here we have some shaping machines in assembly, shaping of big size in terms of OD, so we can produce also this type of technology and machine. And finally, we are having here some of our G160 machine that we have previously shown. To go back to one of the topics of our seminar, which is basically the eDrive. This is the input shaft of an electric vehicle transmission, reduction. So this is the famous part running at a very high speed, which is connected with the spline to the rotor shaft. And this is finally at the end of the machine on which the part will be ground. This is the G160, where you see the two tables, the two linear axes, the main axis, the main spindle assembled on the virtual shifting axis. And this is a project where we will deliver several machines for this type of application.
Okay, what you can see also here that we didn't have any cable in our machine, so it's very easy to clean the machine, and of course we didn't have any wearing cables because here the oil in comparison with the ships and the dressed material from the grinding wheel destroy the cable, and we didn't have this here. So short ways and easy to clean these kind of machines.
Very, very accessible in terms of accessibility, ergonomic access to the machine, dresser, fixture, grinding wheel, or very near to each other. So very usable machine, besides the very high performance and the fact that remain basically the fastest machine in the market for the generating grinding process. So here we have seen, let's say, the applications and some of the machines we have in production. Another important topic is that we in EMAG SU are basically assembly completely some machines. Some others are already produced in synergy thanks to the synergy with the EMAG Group, in particular with the production unit of EMAG. We have already produced together with the production unit in Germany some basic machines, among which, for example, the model of the G160, which we receive according to our design and according to our technology. We receive the basic machine here, and then we tool and test here for the final customer, as we are, let's say, owners as EMAG SU of the technology to grind the gears. So thank you for the attention. I think we are available for questions, and therefore we leave it free to your, let's say, curiosity to place the questions that we might answer. For example, here I see Alex, one of the questions already received, talking about the reliability of the dry grinding process. So how high is the risk of grinding burns? How are grinding burns dealt with? So this is a topic that, of course, comes very, very quick on the table when we talk about dry grinding process. But in this case, what we can say is that thanks to the fact that the grinding is basically only removing a very, very small stock, the law of grinding is very small, first. Second, as already mentioned by Alex, the input quality of the stock for the grinding wheel is controlled and reduced to a minimum level, but very consistent also thanks to the previous sky hobbing process. And finally, more than all of these topics before, we can keep under control each let's say, single vat used to cut in the dry process, because without the oil, each single vat is basically used to cut a micron of stock. So we can keeping under control the power of the spindle very well. We can keep under control the stock that we are cutting, and therefore the risk of grinding burn. So here we have also another question.
But I will add something. So in the to make this absolutely clear, in the dry process we have really 100% process control, because the power we are using in this machine for grinding a gear is related to heating up the gear. And so we can say when there is something wrong in this process, we need more spindle power, and then we can give a signal to the operator. Here you must look, there is something going out, or maybe we have a second deadline where we stop this process, because after this process the risk of burnings are really increasing. So this is the first process where we have a 100% process control to make this absolutely clear. Sorry, Enrico.
No, thank you to you, Alex. Thank you. So next question, can a polish grinding process be combined with topological grinding? Well, we have shown before that both processes are basically working on creating sectors. In this case, you see the sectors that are creating a modification of the profile, and maybe in a later page we see a sector that we have created on a super finishing grinding wheel. So if we can design initially the process so that the sector for the modification is the same as the sector that we glue as a different type, of course we can combine the two. And the only fact that we want to say is that this combination must be designed in advance by the process engineering that we have available for our customers.
So we might have here a roughing, finishing and polishing sector. This means nothing like this. Okay, there is a limitation, of course. This is the phase width and the module. When the module is too big, we are not capable to have 3 sectors on the machine. So we must check this in detail if we have these kind of requests.
Thank you. Next, is the polishing stroke force controlled or path controlled? Well, basically, we control the path of all our, if I understand properly the request, we control, of course, the path of all our strokes, otherwise the quality would never reach the proper target, but we do not really control in the finishing process the force. Is not a process that is requesting a very high force. The only thing that we know is that we must, for this kind of processes, use an accurate process design, which is foreseeing also different behavior of the grinding wheel of a certain grid size in comparison with the grinding wheel of another grid size, or even of another bond like the super finishing bond that has a resinoid bond instead of a ceramic bond. Well, what machining strategies would you choose when alternative? Well, Alex, many questions, so this you can.
Okay, what we can do in these on our grinding machines with different batch sizes. So when we have the tooling, we are absolutely free regarding batch sizes. So when the tooling is there, we can produce 100 parts or we can produce 100,000 parts. This is not a big difference. The only thing is when we have really low batches, we must do oftentimes the setup. But also you have seen before in the G160 also the setup is relatively easy. So when we drive with the grinding head directly to the door, the operator is staying directly next to the grinding wheel and can mount it. The dresser is located here. And when he can go to the load and unloading door, the fixtures are direct in front of them. So also setting up the machine can be very fast. And also here we combine this with a quick change adapter for the clamping fixture, so that we can remove these clamping fixture really in a short time. So also here we have done a lot of development, reducing setup times to compensate smaller batches.
Maybe I also add another point. We have shown you 2 versions of machines that are basically both equipped with a double table solution, so one table in loading area and another table in grinding area. These are architecture that are suitable for a high production. Here we are talking of eDrive, for example, so high production is automotive from a gear point of view, and therefore the configuration of the machine is very important. If we think about lower batches, we also have configuration of grinding machines with one table. And so this is a configuration that for sure can be, let's say, more convenient for a ramp-up of production and more convenient as investment and as changeover time, because it's reducing of the half the time to equip one table instead of two tables.
And also when you must make maybe in a really short time a prototype on the G250, for example, it's possible to use profile grinding so that without any delivery time of special dressing rolls, you can make a part directly. So when
That's correct.
When you want to have a part now, you can do this. This is not a big issue. So we are here absolutely free regarding flexibility, I would say.
Yeah. So no more questions.
Ah, perfetto.
So thank you to everyone for the attention. We are very proud to have shown you our new plant, to have shown you what we have already started to do inside the EMAG Group and how EMAG has integrated in his product line the gear technology, in particular the gear grinding. And therefore, I hope it was interesting, and I hope we can meet very soon in the future and always remain available for contact. Alex and myself, Enrico, are greeting you. Thank you very much for the attention.
Okay, thank you very much also from my side.